Hello friends, today we will do an example of eccentric connection, and in this case my bolt is loaded under shear. So this is a case when bolt under pure shear. So the question says calculate the safe load P that can be carried by the connection as shown in figure below. So we have a figure here and this is my connection. We have to find maximum load P that can be registered by this connection. And what are the other things that is given? So we have been given an HSFG bolts of grade 8.8, diameter of the bolt is 20 mm, and assume that the thickness of bracket plates are 12 mm. And we have to also use the column of type ISWB350. For bolt value calculation, consider both no slip condition as well as slip condition. So we have to consider slip as well as no slip condition. Constants are given. Slip factor mu f is given 0.5, kh is equals to 1, and the plates that is used of Fe410 steel. All dimensions are in mm. So this is the situation we have. So this is my bracket and this is of 12 mm thickness. So my bracket is of 12 mm thickness and this column is ISWB350. So this means I can see the property of this column in SP6. There are 6 bolts and diameter of bolt is 20 mm. So diameter of this bolt is 20 mm. And the grade of plate as well as this plate and this material both are assumed to be Fe410. Friction coefficient mu f is given, kh value is given. So these are the constant that is given. Bolt grade is also given, that is bolt of grade 8.8. So we can calculate ultimate strength of this bolt as well as the yield strength of this bolt once I know the grade of this bolt. Now this eccentricity E, this is given 180 mm, that is the distance from the bolt center line, this line, middle line, to the load, this is 180 mm, and this distance, that is end distance, that is given equals to 40 mm, and this is the pitch distance. So this distance is given and this is equals to 60 mm. So we have been given geometrical parameters and now we have to calculate what is the maximum load P that can be applied so that this connection remains safe. So if you remember, in initial classes we said to check the safety of any system you have to calculate capacity, that is the maximum amount that can be registered by this system, and you have to calculate demand that is coming from the external loading condition, and then you have to compare. And for system to be safe, demand must be less than the capacity, that is basically the amount of load that is coming to the system must be less than the resistance provided by the system. So this capacity is nothing but resistance. So this is the resistance that is provided, and demand is nothing but the load that is coming to the system. So how we find capacity? So if you remember, we can find capacity using code, and in Indian scenario we use IS 800 to find this capacity. So let us find capacity of this bolt. Two conditions we have to consider. One is slip condition, another is condition when there is no slip, and we have an HSFG bolt. So let us consider first to find capacity of an HSFG bolt when there is no slip. So if there is no slip, the bolt will have friction, and we have to find bolt value or the amount of load that bolt can take by considering the mechanism of friction, and that is given in clause 10.4.3. So this gives me how much maximum load that this kind of bolt can take, and that is given in terms of slip resistance, and this is given by this formula, and where mu f is constant, Ne is number of effective interfaces offering friction resistance, mu f is friction coefficient, and Kh is another constant that can be 1.85 or zero point 0.7 depending upon situation, and F naught is basically proof load that can be taken by the bolt, and A and B, where this is the net area. So proof load we can calculate using this formula, where A and B is the net area and F naught is the proof stress that is taken equals to 0.7 times FUB. So let us apply this formula to calculate the slip resistance. So slip resistance can be given by this formula. So I can write here slip resistance, and this is equals to mu f times Ne times Kh times F naught divided by gamma mf. So let us first calculate this term, that is F naught, that is proof load. So F naught is proof load. So we can calculate this term first, that is A N B times F naught, and A and B is the net area at the thread. So if you remember, so we are assuming this thread is under the shear plane. So if I have thread, so this area is A and B, that is basically taken equals to 78% of gross area, that is this area. So in this case A and B is nothing but 78% of pi by 4 into d square, and F naught is 0.7 times FUB, that is given in the code. Now if I plug all this value, so this is 0.78, this is pi by 4, and D in this case diameter of bolt is 20 mm, and this is 0.7, and FUB is 800 because I have a bolt of 8.8. So we can multiply this 8 by 100 and then I can get FUB value, that is 800 in this case. So if I calculate, this turns out to be 137 kilonewton. Now we can calculate slip resistance. So slip resistance, this is equals to mu f, that is given 0.5 Ne. So there is only one effective shear plane. So if you see in this situation, so there is only one situation, one effective shear plane. This is the plate and this is another column flange. So between these two, so there is only one interface that is under shear. So we can put this value n is equals to 1. Kh, let's say this is given in the problem, that is equals to 1, and this is 137. We have just calculated this value and this factor of safety is 1.25. So this turns out to be 55 kilonewton. So you see, if no slip is permitted, in that case this bolt can take maximum of a load of 55 kilonewton. Now let us consider the second part, that is slip is permitted. So when slip is permitted, in that case this will become a bearing kind of bolt. It will not remain as a friction bolt because slip is permitted. Then we have to use clause 10.3.2 to calculate the capacity of the bolt. In that case, this clause says we have to consider shear as well as bearing. So we have to consider shear and bearing, and shear capacity is given in clause 10.3.3 and the bearing capacity is given in clause 10.3.4. So let us first find shear capacity and then we will find bearing capacity. So clause 10.3.3 gives me some formulae to calculate the shear capacity of this bolt. So these are the formula that can be used. In this case, Nn, the number of shear planes that will be intercepting the thread. So A and B is net shear area, that is 78%, and S is number of shear plane without thread intercepting the shear plane, and ASB is the nominal plane shank area of the bolt. So again we will assume that the thread is intercepting the shear plane. So in that case Nn will be 1 and there is no plane, so there is only one plane. So there is no plane that is not intercepting the thread. In that case Ns will be 0. So if we use this, we can calculate B and SB. So let us find a shear capacity. So this is shear capacity and this is equals to V, and basically we have to write VDSB, this is equals to V and SB divided by gamma MB. So this formula. So let us first find this term, that is V and SB, and that is given in this formula Fu by root 3 and N A N B plus NS ASB. Now there is no NS, that is no plane that is not intercepting the thread, so this is equals to 0. So we are left with Fu divided by root 3 and N times A and B. So if I plug all this value, Fu is at 100 and this divided by root 3 and this Nn is 1 and this is 78% of the bolt area, that is pi by 4 times d square. So if I calculate this, this turns out to be 113 kilonewton. Now we can calculate VDSP, that is nothing but V and SB divided by gamma MB, and gamma MB in this case 1.25. So 113 this divided by 1.25, so this is 90.54 kilonewton. So when slip is permitted, in that case shear capacity, I can say shear capacity of bolt, that is 90.54 kilonewton. Now we have to calculate bearing capacity of bolt when slip is permitted. So design bearing capacity can be found in clause 10.3.4. So this gives me a formula for design bearing strength is equals to nominal bearing strength divided by factor of safety, and in this case nominal bearing stress can be calculated, but that is a strength can be calculated using this formula, and where Kb is the smaller of these terms and D and T and Fu is given here. So D is the nominal diameter of the bolt and T is the summation of thickness of the connected plates, and Fu and FUB respectively. FUB is ultimate tensile strength of bolt and Fu is ultimate tensile strength of plate. So you see, if bolt material and the plate material is different, you will have different values of FUV and Fu. So let us calculate bearing capacity of bolt. So we can write that is VDPB is equals to VNPB divided by gamma MB, and VNPB is nothing but 2.5 times KB times D times T times Fu, and this divided by gamma MB. So let us first find term KB. So kb is what we have to find minimum of. So we have to find minimum of E by 3d naught and P by 3d naught minus 0.25 and FUB divided by FU and finally 1. So we have to find minimum of all this. So this is equals to minimum of, and in the distance is given in this case, that is 40 mm. So 40 divided by 3, and the bolt diameter, that is the nominal bolt diameter, we have to add 2 mm. So this becomes 22 mm. And this pitch distance is given, that is 60 mm. So 60 divided by 3 into 22 minus 0.25, and this is for bolt. So for bolt we have 400. Now FUV value for this bolt is 800 because we have a grade of 8.8 bolt. So this is 800 divided by 410, and this term is 1. So we have to find minimum of all this. So if I do this calculation, so this turns out to be 0.606, and this is 0.66, and this is 1.95 and 1. So minimum of this is 0.606. So kV value is 0.606. So now I can put this kV value and we can calculate VDPB. So let us calculate this value. So VDPB, so this value is 2.5 and this kV value is 0.606, and this is 20 times 11.4 and divided by factor of safety or partial factor of safety, that is 1.25. So in this case 20 is the bolt diameter and 11.4 is the thickness, and we have to consider thickness T, that is given in this formula, which is basically equals to minimum of two things. So we have to consider flange thickness of ISWB 350, that is the material or section of this column. So flange thickness, that is ISWB 350. So this we can find, this thickness value we can find in SP6. And then we have to also consider the plate thickness. So plate thickness in this case is 12 mm. So this was given in the problem, that is 12 mm, and if you look SP6, this value is 11.4 mm. So we have to consider minimum of this two, that is 11.4 mm in this case. So if I calculate this value, this turns out to be 221 kilonewton. Of course, here I have to multiply by Fu, that is in this case 800. So you see the initial formula also has Fu. So we have to multiply by Fu and then we can get the strength or capacity in this case, that is bearing capacity of this bolt. So this is bearing capacity. So we have calculated bolt capacity when we have no slip and when we have slip. Now we can calculate now what is the minimum force that this bolt can take, that is also called as bolt value. So we have to find bolt value, that is the amount of force that this bolt will take, that is nothing but minimum of the force that it can take under no slip condition and the force that can it take under slip condition. So if you remember, in case of no slip condition we calculated that this bolt that is becomes a friction bolt can take an amount of 55 kilonewton that we have earlier found this value. And then under slip condition we found there are two cases. One is shear case. In that case it can take 9.54 kilonewton. And then we said that when this becomes a bearing bolt, it can take a value of 221 kilonewton. So minimum of all this, that the bolt can take a load of 55 kilonewton. So now we have calculated the capacity, that is capacity of this bolt is 55 kilonewton. Now I will focus on the second aspect of the problem, that is demand, and at the end what we have to do, that is at the just boundary we can say demand is equals to capacity, and then we can find value of P. So let us calculate demand in this case. So if you remember, in the previous video we discussed calculation of demand in this case, that is the amount of force that will be generated in any bolt. At that point of time we said this is an eccentric connection that has basically shear force as well as moment both. So at that point of time we said we can break this problem into two parts. First is shear and another is, so this is a case of pure shear, and then we said we can also break in case of pure moment. So we will consider this problem as a pure shear and pure moment. So if I consider pure shear, this amount P will get transferred to this bolt and this bolt. So equally it will be divided in 6 of the bolt. So due to this direct shear, the force in each bolt that will come, which is equals to P by 6. So due to direct shear, I can say force generated in each bolt. So force due to shear. So this force is equals to P by 6. Now we will consider pure moment case. Now in this case, this force will apply a moment, and that is equals to PE. So my moment is equals to P times E. So if you remember, in the previous classes we said due to moment these forces will be tangential. So this will be in this direction on this bolt. Sorry, this is the CZ is here. So I have to take the CZ. So this is the CZ. So in this direction on this bolt, in this direction, and on this bolt this will be in this direction. So these are the forces. Similarly on this bolt in this direction, on this bolt in this direction, and on this bolt this will be in this direction. And the magnitude of the force we have derived in the previous class. So direction we just shown, and the magnitude can be given as, so magnitude in any ith bolt that can be given by this formula. So Fi is equals to P times E divided by summation of dis square and this times di. So this is the force in any bolt. So let's say if I consider ith bolt, I can calculate force, or this is basically shear. So shear force due to pure moment. So each bolt will have different force value. So what is the critical bolt? So which bolt is the critical? So we have to find which is critical bolt, because the critical bolt that will have maximum amount of force is going to fail first. So now the first thing is critical bolt will be one which has maximum amount of force, and in other words it has farthest from the neutral axis or center of gravity in this case. So this bolt, let's call this is bolt 1, this is 2, and this is 3, 4, 5, 6. So you see bolt 1, 3, 4 and 6 is the farthest bolt. So these bolt will have maximum distance and these bolt will have maximum amount of force. Now if you also include the direction, in this case, let's see this bolt number 3, the force due to shear and the force due to moment both are in the same direction. In this case also this will basically add, but in this direction in this bolt, that is bolt number 6 and bolt number 4, it will subtract. So bolt number 1 and bolt number 3 are the critical bolt, because in these cases force will add. So the component of shear, that is pure shear, and component of pure moment will add, because those are the forces in the same direction. If this is not clear, I can show here. So this is bolt number 3, this is bolt number 1. So if you see on bolt number 1, this force and this force, so these two forces will add. On bolt number 1 also, this is in this direction and this is in this direction. These two forces will add. But if you see bolt number 6, one force is in this direction but other force is in this direction. So they are having in cancelling nature. So these two forces will subtract. So I can say either bolt 1 or bolt 3, these two bolts are critical bolt. So critical bolts are 1 and 3. So let us find, basically in this case both bolt will have same force. So let us calculate for bolt number 3 the total amount of force that will be generated. So I can draw this. So this is my neutral axis and this is my bolt number 3 and this is the distance, and in this case this force is coming due to pure moment and this force that is coming due to pure shear, and that is nothing but we have already calculated. This value is P by 6. Let's call this angle as theta. So this angle will also be theta, because line between perpendiculars is angle between perpendiculars is equals to angle between lines. So if you see this line and this line, angle is theta, and perpendicular to this line is this line, and perpendicular to this line is this line. So this angle is also theta. So now I know geometrical parameters. Now we can calculate the resultant force, but before that we have to calculate force in bolt number 3, that is F3 is equals to P times E divided by summation di square multiplied by d3. So if you see this distance is given, in the problem. So this distance is 50 mm and this distance is 60 mm. So if you take a square root, sum and a square root, then this will come 78.1 mm. So this diagonal distance. So now we can calculate this value. So this value will be, P is given to us. No, P is not given, E is given. Eccentricity is 180 mm. And this is summation of di square. So I can say 4 times. So you see this distance is equal. So centroid from bolt number 1, bolt number 6 and bolt number 4 and bolt number 3 is equal distance. That is 4 times of this distance, and 2 and 5 is also equal. That distance is 50 mm. So 2 times 50 square. So we can write it here. So that is 4 times 78.1 whole square plus 2 times 50 square. This is multiplied by 78.1 mm. So we have 0.478 times P. So this is the value of F3. Now once I know F3, we can calculate the resultant. So this force is F2, that is P by 6, and this force is F3. that is 0.478 p, and this angle is theta, so we can calculate resultant force. So resultant force in volt, so this is nothing but we have to use formula p1 square plus p2 square plus 2 p1 p2 cos theta. So this is p by 6 whole square plus this is 0.478 p whole square plus 2p1 p2, that is 2 times p by 6 times 0.478 p times cos theta, and this cos theta is what? Cos theta is this, that is 50 divided by 78.1. So if I plug this value 50 divided by 78.1, and if I simplify, this turns out to be 0.478 p. No, 0.599 p. So this turns out to be 0.599 p. So now once I have this value, that is nothing but my demand. So this is the demand. So we have calculated demand, that is 0.599 p. So in the end, what we can do is we can equate my demand with the capacity. So if I equate that, demand is 0.599 p, that is the force that is required in this situation, and the maximum amount of force that bolt can undertake, that is capacity, that is 55 kilonewton. So if you solve this p value is 92 kilonewton. So to summarize, in this lecture, we discuss one example related to eccentric loaded connection. In case of eccentric loaded connection, we first have to consider demand and capacity, and the capacity we can find using IS 800 or any other code if you have similar problem and similar code, and then demand you can find using the actual situation, that is the load that is given in the field, and once you equate demand and capacity, you can basically calculate the unknown forces that you can give to this system. Similar problem can also be framed in terms of design. In that case, you have to use capacity and demand, but in that case you will also basically iterate to calculate the total number of bolts and pitch distance, in distance, all this thing will come there, and you have to make certain assumptions so that your design basically satisfy the demand. Thank you.